Good morning, everyone. My name is Renee Fippin with Delve Underground. I'm co-chair of the DFI Tunneling and Underground Committee with Bob Steer, my co-chair. Welcome to our webinar this morning. This is our second webinar. We held one last year, and we hope to continue. Angelina, next slide. Okay, I'm going to go through some housekeeping rules before our presenter begins. During the webinar, all attendees will be muted. The Q&A will be following the presentation, not throughout. And if you have a question, you put it into the Q&A box that is on the bottom controls of your Zoom screen. And then I will read them at the end, and Shawn will answer the questions. Next slide. PDHs are available for paid registrants, and you can actually even pay afterwards. And you complete the webinar evaluation. So you get a web link, and that will be sent to your email address. You can register for all other webinars at dfi.org. Please give feedback or suggestions. We'll have to plan next year's webinar. So if there's a topic you want to hear related to tunneling and underground, feel free to email myself or Bob or events@dfi.org. I'm going to introduce our speaker, Shawn Drobny with Ballard Marine. Shawn is a licensed professional civil engineer with over 17 years of experience in heavy civil tunneling and underwater construction. He's one of the lead engineers at Ballard Marine Construction and has worked on several billion-dollar projects with complex engineering challenges, including tunneling, utility support, traffic decking, and drilling in downtown LA. He's been design coordinator for 3 large supportive excavation designs to support underground subway stations with steel decking to support live traffic above. And for this project, he's recently managed the research and development project for Ballard, which is the project he's speaking about today, where he helped develop one-of-a-kind patent-pending diver-operated underwater tunnel ring forklift. The new technology allows tunnels to be repaired underwater without taking the tunnels out of service. Shawn actually came to our offices last year and presented, and you can tell the project is incredibly fascinating, and you can see his engineering love as he speaks to us about it. He oversees all engineering support for large and complex projects for Ballard Marine. And I just also want to add that Shawn and his wife recently had their 3rd child, a daughter, 12 days ago, and he was kind enough to agree to this webinar and is presenting with that in mind. So we thank him very much. And with that, I'll hand it over to Shawn, who will take control of the screen.
Thank you, everybody. Can you see my screen? I think it should be working. So my name's Shawn Drobny. I'm with Ballard Marine. It's a sister company of TCG, which is the Trailer Construction Group, which we're a part of. And I was with them for 13 years, and then I've been with Ballard for 5 years. And so this is one of a kind of a very interesting project that we were involved with, and we'll kind of get into it. We always kind of start our stuff off with a safety meeting. This one kind of relates directly to the vehicle itself. This underwater vehicle is, basically 3-phase power, 900 volts, in fresh water. So that inherently is a concern when you're a diver working next to something. They do a lot offshore in ROVs and stuff like that. But saltwater obviously is not as problematic as it is in freshwater. And working with what you'll see in the presentation, working with deep sea ROV companies and stuff like that, freshwater was kind of a new thing for everyone in this realm. And so there was a lot of things that we had to think about from a safety standpoint. And we actually, in every iteration of it, we actually included safety as the #1 thing. And you'll see we've added additional air canisters on the side of the vehicle for the divers to give them 3 additional hours of bailout time and those type of things. So when I go through the presentation, like you said, safety was probably the biggest thing, and that's what really was pushed the development of the vehicle. So kind of move on. So this is kind of a picture of the project itself. I'll get into the project a little bit, but just from this picture, you can see the team of divers it takes to run it. The project is actually in Detroit. We did most of it from the median. That's about 34 feet dimension from curb to curb there, and that's where the pipeline runs in there. But this is kind of the team that helped develop BERT and ran it for the very first time. And so very, extensive divers, and you said they have their experience is amazing, and working with them through the R&D process, they kind of helped us develop the vehicle as they would be the ones working by it. So let's get into the why. So, like you said, the aging infrastructure in the United States is something, that everyone's aware of. And a lot of these things, like the tunnels that we're going to talk about today, were built back in the 30s and the 50s. And some of these are seeing some complications and some challenges, maybe not as bad as the picture on the left. But again, it's how do you fix those things? And then how do you do that in a situation where, you may not be able to shut it off or bypass it in a very easy way. And so that's kind of what this project, how it came about. So if you know Detroit, kind of looking to the north, there was actually 3 tunnels in the system that we worked on for this contract. Our designers were Brierley and Schnabel. Schnabel was more on the liner design than Brierley the overall project. There was 3 tunnels throughout to 2 of the ones that actually got the liners, and then we did grout injection for crack injection in one of the larger tunnels. But that's a little over $90 million. And like you said, we're in the last year of it actually currently right now. So the inspection, so how did we get to this project? We first got out there for the inspections of it. We used divers in 2015, 2018, we used divers as well as ROVs to do a full inspection of the whole system, which is in, excess of 10 miles for each tunnel. And doing that, there's certain instances we used ROVs, some instances we use divers. Some of these divers, they were penetrating over 2,700 feet to do the inspections and gather the data to even see what was wrong with the tunnel and what we could find. So the first tunnel, the 12-foot diameter, was built in the 1930s, unreinforced concrete and cast in place tunnel. And soft clays. As you're going to see in a slide below, they kind of hover just above the hard pan. The second was in the 1950s, same soils, about 95 feet down, and we'll kind of get into that. And that kind of proposed, definitely put a challenge on us. And there's a two liner system on that with auroric blocks on the outside and then an inner lining, whereas the one above in the 30 was beam and lagging and cast up against that. So those are the kind of the descriptions of kind of the 2 tunnels that we were working on. Here's kind of a quick showing where the tunnel kind of lies. It basically in a profile, it kind of hovers around the hard pan, and this kind of is what led to a lot of the cracking in the tunnel, is that variance in the soils and stuff like that. So this is between that river till and then the hard pan. That's kind of where the tunnel just kind of, like you said, hovers as they went. Again, there are accesses into the tunnel. Like you said, they're very far spaced out, and that's where we had to use divers as well as ROVs to map and see the tunnels. You can kind of see from this slides that the tunnels, significant longitudinal radial cracking, and definitely there were spots where the soil was infiltrating into the tunnels, and some, rare spots. The goal for the owner was to allow this tunnel to be dewatered, so that traditional repairs could be made. But with this inspection, the fear of dewatering it, the fear of that would lead to a collapse possibility. They tried to dewater it, too much infiltration, or just a pure structural problem with the tunnel itself. And obviously that goes back to our safety stuff, risk to personnel, the tunnel itself. The entity could not afford to lose a tunnel. Obviously, this applies, a majority of the water for the entire Detroit area. So you can't take it out of commission because the capacities required are just too much, and the fear of the collapse is too much. So what does that bring us to? That brings us to how do we get in there to do, these repairs in these areas where the cracking is really bad and that we wanted to repair. We kind of sat down with the owner and, is there the drive, could we bypass the tunnel? And you kind of see the picture above with the pumps, but that wasn't feasible in any, given the capacity of these large tunnels. The pumping requirements would just way too much and costly for that. Our proposed in the wet repair, that's eventually what we went with, what we talked the owner into, is doing this repair that we're going to talk about. Obviously, coming from the trailer construction group and the tunneling group, we know the cost of putting in new tunnels, and that they weren't too interested in jumping into that market of spending that kind of money to replace these two tunnels. So that's kind of what led to this working in the wet, not taking it out of service, and basically making these repairs in the wet, which was there. Now we looked at, we talked about traditional liner plates, galvanized liner plates. Obviously they're light and easy to move, but high bolt count. This is very problematic in the marine diving world because obviously we had limited time as a diver. Depending on how hard they were pumping and stuff like that, the depth of the water can range from 65 feet. And so that only allows a diver in the water about little less than 2 hours diving on a nitrox gas. So again, every bolt count, the time it would take and stuff like that. But in the end, the traditional liner plates would not work because of the design requirement that I'll get into here in just a minute. So the repair was in a kind of call it a structural solution. The liners had to withstand 95 foot of hydrostatic head, and a 50-year design life. You think about that, it's 304 stainless. And when we get into the liners, you're going to see that this is in millions of dollars in custom stainless steel liners that would need to last that 50 years. I have a slide later where we talk about, how do you do quality control in something like this in an environment where, you can't send your field engineer down to do your quality control. So we'll kind of get into that a little bit too. And the best thing was, we didn't want to take their hydraulic section down. And so again, we went through a lot of iterations of what these tunnel liners would look like and trying to keep that to a very small thing, yet give us enough room for the installation. And so this is kind of like I said, we've developed this basically with a mix of engineers, managers, divers, fabricators, everyone I kind of managed in the R&D team to both come up with the liners as well as the vehicle. And you kind of see that. So the designer definitely did these FEM analysis on the tunnel, both the penetration that I'm going to talk about actually comes through the liner section. You see the picture on the right, that's kind of the connection between the liner plates and the access shaft. It's a pretty complex stainless steel welding and fabrication there. And those are the small liners there. And so that's really what they were checking with the analysis, making sure that how we transfer loads and everything through the liners. That's kind of what the designers were doing. So how do you do this? So the pipes, like you said, total length is 1,200 feet. One tunnel was 500 feet of repair that we came up with, and the other was actually 755 feet repair. So it's actually two different sites. The problem with that being is that those repair sections weren't close to an existing access. And so how do we get the tunnel liners down there? How do we get the diver down there safely? We had to actually install and drill into the existing tunnel in a location so that we could service the work effectively. Like you said, if the divers and everyone had to penetrate the 1,800 feet or whatever it was to get to the repair section, they would have limited time for the repair to actually happen. So again, it was decided that we would patch into the tunnels, which had been done before. But again, it's very, like you said, a risky part of the project. But again, was required both we decided that the divers needed their own access shaft that was smaller, and then a larger access shaft that was just for materials and actually what would be the vehicle itself. I slipped this in here for the quality control, and just to, if you're not familiar with the diving world and how this works, the actual field engineers sit in the dive control, and they are going through this with the diver, taking pictures, using video communications, and using this checklist for every single liner plate we installed. Whether what the gaps were, what the annulus measure was in different locations, the bolt count, the torque, there's a torque requirement on all the bolts. But again, this is the QC sheet that we used to verify, that quality control was there and assure the owner that that was being done. So let's get into the project. This is kind of the riskier part, and kind of something that was, like I said, piqued my interest was, how do we get into the tunnel and how did we do it? So from the surface, we had a subcontractor and Ballard drill down a 9-foot inner diameter casing just 1 foot above the tunnel crown. And from that, we left a soil plug in there because of, water infiltration and stuff like that. We kept the tunnel or the shaft, filled with water. And then basically the last part of it was diver access. We were able to get the divers in. We came up with a digging shield. We call it a digging shield, kind of like just like any kind of shoring. And the last 5 to 8 feet ish was hand excavated by the divers. And as they did that, the shield would kind of follow the casing until they reached the top of the tunnel. And that basically gave them protection from the outside. Once we did that, when we were able to clean that entire thing off, we poured a leveling slab that basically followed the crown, but leveled that thing up so that the drilling contractor would have a nice flat place to start coring. So we put a form up, we cast that, and then basically when we cast that, we tied it into the casing itself, making a very good, strong connection between the casing and that concrete seal pour. And then basically that created like a template for the driller just to land his core barrel inside that and then core through the tunnel. The picture on the top right shows kind of the start before we would core it. And you're asking, like, you can imagine that a 10-foot diameter inner diameter tunnel, and we're drilling an 8-foot core out of it, doesn't leave a lot left in the tunnel itself. So the designer, came up with this. We basically had to install these rings that were tied together with tie rod. That created the strength needed to do the core and push that crowd force. It was a very long process to core through because we didn't want to apply a lot of force down on the top of the tunnel. So again, then we cored through, and you're asking how did you get in there to do the ring installation for that? We did do an initial 18-inch core to allow us to feed the materials down, but the divers actually penetrated about 1,800 feet in and assembled these in a very slow process to assemble the rings and stuff like that without access. So we did that for both tunnels. You can see at the bottom side, you got your larger access shaft, and then we went down to a 3-foot shaft for the diver access shaft, and they're about 30 feet apart. That would give the divers and their umbilicals and stuff like that the ability to go down that shaft, and then all our materials in the vehicle would come down the larger shaft. So that's kind of how we did that. Then to transfer the loads through it, we put down a 1.5 inch stainless steel casing down. You can see it has tabs where it was able to land on that concrete, and then we had the diver scribe it, pull it back out, and cut it to fit. And then once we did that, we had pre-placed bevel washers on all the sides where we were able to anchor that into the actual tunnel crown. And then we grouted the annulus between that. And that was a good structural connection, allowing us to remove the internal shoring and start the project. This is a picture. This is kind of the slides for the liners. You can see this handsome guy over in the right-hand corner here. I'm about 6'4", standing in the 12-foot inner diameter tunnel. Those are the liners themselves. Again, Schnabel Engineering did the design on the liners. We worked, we started off, obviously, when you're using that kind of linear footage, every pound counts for every liner. And so we actually started with a 3/4 inch skin because of the loading, but we're able to add some stiffeners. We used 3.5 inch by 1/2 inch angle as the flange connections. And so we're able to get that skin down to a more manageable, I think it was 1/4 inch, which definitely, took our weight way down. But again, those are the custom liners made. Now, if you're not familiar with stainless steel welding, you can get a lot of temperature variations when you're doing that. And obviously there was a lot of weld required because of the internal stiffeners and just making sure that was all, tight. You can see down in the bottom right is the jig that they had to make in order to hold our tolerances. They started off with something smaller, but in the end, we weren't getting the tolerances and we were having trouble mating them up. So they had to get something more robust to hold it during the heating process to hold our dimensions. And then you ask, how do you hold that 4.5 inch annulus gap? We came up with an insert that goes into a 3.5 inch coupler, steel coupler, stainless coupler, and it basically inserts there, and then that leg kind of pushes out to a swivel foot. And by adjusting those 6 jacking screws, the divers were able to move the ring around where they need to hold the annulus of the 4.5 inch. It would be perfect if the tunnel was perfectly, a perfect circle, but it wasn't. So we were constantly trying to find the center as we would march and install the rings. And so to do that, again, these jacking boards came in handy. They not only support the ring, but they actually help hold the rings to the vehicle itself as well. Now the grouting ports, there's 15 grouting ports. We actually we spaced these grouting ports up to match up to a pour sequence that when we would grout the annulus of the liners, we would pour to one and then there'd be a lookout for the other, and so that we could see where the grout was going. So we actually spaced these the grout ports to the grout port levels. Now we would have loved to pour the whole thing at one time, but the loading on the rings during that operation actually was the design constraint for the construction of the rings and the design of the rings because of the loading on it. So we had definitely 5 individual grout lifts as we went through. And then we weren't really sure how far the grout would flow, how well it would flow. So we basically broke up the sections into 50-foot sections. And then we had bulkhead rings at each section. And we used actually a custom, from Mechanical Research, an inflatable bulkhead that I'll talk about a little bit later. And that's what would cut off each bay. We would grout those, and those rings actually got, as the picture on the top left, those are bulkhead rings where they have additional stiffeners. They have one more jacking leg just to give them the strength to pour that in one continuous. So, but they were substantially heavier than your normal ring. So that it was working with the fabricator, doing a lot of that stainless steel stuff. But I think the key to this project was the owner allowing us to do mock-up. We mocked this up for about 3 weeks. We used the divers and the dive supervisors and the engineers, and we met for 3 weeks on how do we install these? How do we get with our access that we have, how do we get this? And one of the key things that came out of that is kind of what this picture shows, is what we call the football method, which is actually part of our patent. And that football comes down, it opens up, and then we add the third piece, and then we bolt those rings up. But it was this mock-up was key to finding out what the bolt sequence would be so that we weren't under suspended load, and getting that, with only having 4.5 inches around the whole thing, having enough play to actually open up the ring and assemble it. The mock-up was the key to our success in this project and developing not only the liner installation, but actually the vehicle itself and figuring out how we were going to do it. So that comes so now we got the rings. We understand how heavy they're going to be. They'll be 4,000 pounds a piece. We wanted to get production. We wanted to get 2 rings. And so how did we do that? So we put together, with the help of the Trailer Underground Division, and Kelly Engineering, we started with concepts. And they went from simple to a lot more complex, from simply just putting on a roller system and rolling it down the tunnel, which gave you no stability, gave you no ability to control the rings, but we thought we could get it down there. Traditional methods of doing this was just putting lift bags underneath the liners and moving them by hand with divers, which is very, time consuming, as well as, not very safe, and moving, traditional liner plates versus something that's 4,000 pounds, significantly different, a lot bigger lift bag. So this is kind of where we went with it. So then we kind of said, hey, we got an ROV, division of the company, and we worked with some overseas designers, and relatively the Kelly engineered equipment is who built BERT. But working on these first initial concepts, we said, hey, what if we powered the vehicle? What if we went from a cart, something that just going to be moved by hand here in the simple one, concept two, to going to something that actually has a hydraulic unit on it that can move it hydraulically so that we don't have to crank it and stuff like that. So we kind of start with some initial designs. And then as we worked our way through, it definitely started improving and got to a point where it was a very full design of what BERT is today. So this is kind of what it looks like in the tunnel. You can kind of see the liner. This is how the vehicle kind of attaches to the rings. It uses those same jacking ports. It can actually hold 2 rings at a time. So it's actually, it has the capacity with the counterweights that's on it to cantilever, 2 rings at a time, which is about 9,000 pounds. So this is kind of what the vehicle looks like. You can kind of see the taper to the wheels to fit, the tunnel and run in the tunnel. So let's kind of get into the details. What happened in the end when we found that we were kind of developing a new technology, and that this could be something huge for the company and moving forward. We started early on in the patent process, and if you've never been through this takes way longer than you would think. But again, we not only, looking through what was already out there, we were in our league of our own as far as the patent itself. So we were able to get a very broad patent on the vehicle, as well as the ring installation process itself. So that kind of led to the patent, which was pretty exciting, as well as our patent actually covers some of future attachments that we haven't even actually created yet, as far as tunnel dredging, tunnel cleaning attachments, and we'll kind of get into that as well. So how does it work? BERT breaks down into 6 major components. We knew we weren't going to be able to get a 25-foot long vehicle down the tunnel like we wanted, not in one piece. So it breaks down into these kind of big segments, and then basically it goes down. You put the main body first, you connect the tail section and the operator station, and then the arm sections and everything kind of go down together. It can fit down a 7-foot diameter shaft relatively easy. And again, when we first started designing this and going through it, we thought that, this process could take a week to assemble it. And, and obviously the first couple of times it was quite extensive, but today in this year 3 or whatever in the project, we assemble this thing in a shift. It goes down, assembled, ready to go in a shift, which is about 9 hours. And it's fully ready to go. So that again kind of changed our design, is that we first started off with a lot of hydraulic QDs and stuff like that we could change stuff underwater. And in the end, if we do have a problem or something we fix, we just literally take it out in the shift, repair it, and put it back the next day. So that kind of worked out really, really well. One thing to consider when working in a tunnel is that the owner was not going to be able to necessarily shut off because of their water requirements. Our dive season is from October 1st to May 1st, give or take. And that is because they're able to supply enough water and shut it down in maybe a 10-hour window at night, which is when we were working. But even then they would keep one pump on, and so that there'd be definitely flow in there, and there is constantly flow in there. So we wanted to know what is going to be the situation. The divers, we don't like to see over 2 feet per second. It gets cumbersome to work in, and not safe. So we did some flow analysis and figured out that, it had a very minor delta and change, although it looked like it was taking up a lot of the cross section. We had a very small change in velocity through the liners because of the vehicle. Now, the divers will tell you that they definitely can feel the difference when they're inside the liners versus outside the liners before the vehicle. But again, it definitely is holding true to this flow analysis. This is kind of a video. It kind of depicts the stages. It's kind of a long video, so I'm going to kind of walk through the steps here. But again, this is kind of the overall project. You got your shaft. Our water head was about 65 feet. You essentially, the first thing to come down is actually the football section that's lowered down by the crane. And again, it's all about the rigging and how that works. And then it comes down and lands and then kind of opens up into what we call the football method. So it kind of opens. Now you have room above you for the divers to work, but it kind of opens up. And then again, we repeat the process with the third liner. The third liner does have to be landed and then re-rigged and then brought up into location. So it lands, the crane re-rigs, we bring it back up, and then we use come-alongs to bring it back together, land it, and we make those 4 initial outside bolts to make up the initial ring. And once that's done, the vehicle comes in and it actually goes to the first section, ring 1, and it will attach via those jacking boards with those jacking inserts. And it will basically attaches there. And those same 3/4 inch screws is what attaches the ring. Now, this first ring, because we wanted the joints to be opposite of each other, this first arm can rotate 60 degrees out and attaches and then spins the ring to a level position using by keeping the ratchet attached and making the hydraulics. It's able to rotate it just by coming up on it. And so it rotates it into position. The divers then drive the vehicle back and move it out of the way. This second section, the front section, can actually move, so you have separation between the rings. The same process happens, except for this one's on the normal. And so now you have an A ring and a B ring, and the joints are, like I said, there's 120 degrees separation, they said, for design strength and that type of thing. So again, it raises, it again connects, it brings that together. That's the most time consuming thing, is doing the circumferential joint bolts and bolting all that up. But once that's complete, we now have 9 feet of completed ring that the divers basically drive the vehicle down and install it and kind of work our way out. And so by using the vehicle, we're able to control that entire 9 feet up, down, left, right, until we made it up, kind of like mating up a space shuttle. You made up that joint, that flange, and then that bolts up, engage the jacking bolts, and that's kind of the sequence. You can kind of see the ratchets that bring it in and out. We wanted some fine control for that, as well as the rotation, so that we could kind of see if it was binding up, and that's why we did not make that hydraulic. So that's kind of the process. So what are the controls? So basically, it can move up, forward, back. The divers have control of the reel that actually has the umbilical on it, and as well as we've added stuff now that we can control hydraulic stuff on the front of it, kind of like a skid steer. But again, that's kind of how it works. It has rear steering like a forklift. Again, because the vehicle is 25 feet long, minor steering adjustments at the back is a big transition at the front. So again, we wanted very fine controls and be able to move very incrementally, especially coming up and matching up to the rings. That spool that's on the vehicle actually keeps a 200-pound tension on the umbilical, so it's always tight and always winding correctly, so you don't get any spidering or anything like that. The heart of the vehicle itself is an underwater HPU unit. It's 480 volt, 3-phase, 900 volts out to the vehicle. It provides we run it typically around 3,000 PSI, which is more than enough to control the vehicle. This came from a large ROV builder, deep sea ROV builder. Obviously, it's not a traditional HPU unit, as in this is a completely sealed system, which, definitely has its own benefits and downsides to it that we'll get into. But the vehicle itself, fully intact is about 20,000 pounds. So it's basically a tank. It was about a telehandler, you could say. So it's very heavy, but again, it has its four-wheel drive. Each of the drive motors, with 9,000 pounds of ring on it, something like that, this thing is almost unstoppable as far as its power. And although slow, it basically can creep along as even in flow and current and stuff like that with rings on it. So it's very, like you said, this vehicle is, when we started, could do 2 or 3 miles an hour, what we didn't want to do. We wanted the divers to have to, very slow and not have some of those issues. So we actually turned the HPU down in pressure, so we have more capacity than we need. But again, we had to slow it down, and about a half mile per hour is kind of what it rolls, and you'll see that kind of in the video. The other question that you might think about is you're working in what was raw water, but they were holding us to drinkable water, NF61. And so how do you do it with this hydraulic system? And what we did is we had to work with the suppliers and stuff, with the purities and the Schaefer and your bio oils, and working in temperatures of 33 degrees to 60 degrees and getting that same performance in that temperature variation throughout the dive season. So that's kind of where we definitely, like I said, use the shape. I think we were at Schaefer's and Purity. We've danced back and forth between the two. So another cool innovation that we were super happy about is basically this is like a skid steer. It has the front of it has 2 hydraulic cylinders as well as 2 control cylinders. We're able to run all of our Stanley hydraulic equipment off that. That was kind of a huge innovation as itself, as we thought we would be doing all these bolts by hand. I think there's 36 in the circumferential joints alone. But as you can see in the bottom right picture, we're actually using impacts. Once they're hand threaded, obviously stainless bolts can gall and stuff like that. But once we get them threaded, the divers are using their hydraulics to impacts to put these bolts home, and that worked and definitely increased our production. So. Some of the kind of other cool innovations with this is how the vehicle works is kind of we thought of it more of the Cadillac stuff, but actually came to fruition. It was really an integral part of the system. Is it has 2 cameras, one forward and one aft. Those cameras are shown in 2 underwater monitors that I'll show you here in a minute. And then it has 8 individual lights around the vehicle and key component parts so that we can light it up. As you know, if you've ever dove, when the water's really clear, lights are fine, but when it's really, 6-inch visibility, light can actually hurt you. And the other thing that we came into is in a stainless steel environment, the light is refracting off the stainless, and it can get very, very cumbersome. So with working with the DFC company, we were able to individually change at the surface the dimness of the lights. The field engineer can adjust those lights, and we can also preset for different operations the lighting sequence for ring construction, driving forward, driving back, and we can kind of change those. So that was kind of cool. All that goes through a slip ring. If you don't know what a slip ring is, it allows all those connections to rotate and be both the power, the video, the serial, all those things rotate in this disc and allow it to transfer into a rotation, which is the reel up on the bottom, top right. And then you have the control canister there on the bottom right that holds all the power requirements. The HPU and the lighting and the cameras are on separate deals. So if one were to go bad, we still have the other. So again, like I said, a lot of the safety things put in there. So how does the vehicle work? I want to tell you, you got to put yourself in this environment and what these individuals are working in. In the tunnels, this is in our testing stuff, so it's nice and clear, but in the tunnels, we're diving from October to May. The temperatures are typically, 33 degrees and a little above. So we're in, freezing type water. The visibility can range from 6 feet visibility down to commonly 6-inch visibility. And so how do you drive a vehicle when you can't see it? That's where these underwater monitors came into it. And so that forward-looking camera is facing down. It uses the joint of the ring, and we pre-placed a centerline, yellow centerline cable down the tunnel so that we could use that for navigation. From the rear camera, you can see the umbilical of the vehicle, which is only 3/4 inch that everything goes through, which is fascinating to me. And so basically the diver is putting their mask and watching those two underwater monitors, and that's how he's holding the center line and driving the vehicle. This was not something that we thought we would be using a lot of, but in the reality, it came to be almost essential for us to navigate the vehicle in these kinds of conditions. So from start to finish, from a first pencil drawing to the vehicle fully fabricated and completed was 10 months, which is astonishing to me, and I think most people I talk to. So 10 months, and then we had to find a place. How do we test an underwater vehicle and where? I searched all over the country and places to test it. In the end, testing it in a river or on a boat ramp or something of that nature was not feasible due to the weights and stuff like that. And we also needed the ability to put a crane to lift this vehicle and put it into the channel itself. I ended up coming upon the Hinsdale Wave Lab at Oregon State University, which was perfect. It's 12 foot. It's basically 12 foot wide, 15 feet deep, 324 feet long. There's only one other channel in the US that's bigger, and it's only by a couple of feet. But again, this provided us the perfect place for us to test the vehicle. Not only they had shore power, but we were able to sneak in a 35-ton crane into the facility in order to lift the crane and safely test it. So I'll go through the kind of the testing pretty quickly. We installed up in the upper right-hand corner a host tunnel to be our practice tunnel. We kind of had to make some wood to kind of mimic the tunnel itself. But again, that would be our docking location. That's where we would practice making the connections and moving the rings around and try and figure this out. We used the divers that would be in the water actually doing this because they would be the ones in the environment, and they also had great ideas of what they're going to need in that environment. We did start off, we designed an HPU that goes on the back to provide power to it because the actual HPU is only designed for being submerged in water to cool it, and it overheats in about 5 minutes. So we had an HPU that would do it, but we didn't get the same flow rates and all those things. So in the end, we came up with a very sophisticated design of running a constant garden hose over the unit to cool it, which allowed us to eliminate that, the noise, the smoke, and we ran the vehicle under its own power. And again, the divers just practiced, and we definitely recorded like what things we needed to fix, things we needed more play in, and basically we honed in on the dry testing of it. And once they were all comfortable with that, that's when it came to testing it in the water. Obviously, before you get this unknown vehicle in the water with the divers and this power and all those things that we had to deal with, we ran through all the safety checks, checked for every leaks, checked for electrical things, making sure everything's tight, and really honing in on that to get its first dive. So we first lowered it in the bottom of the channel. The channel fills in like 12 hours, which was pretty cool, in hydrant water so that we could work in pure, clear chlorine water. So you can kind of see the pictures from above. We were able to, like I said, see a lot of it and work with it. So one of the scariest parts of my career was, like I said, we're going to ask a diver to get into this with this vehicle for the very first time, with this voltage, fresh water, all these things. And so we did a lot of checks. We had a lot of stray current detectors on the surface to see if there was any stray current actually detectable. There wasn't. So we turned the vehicle on by itself, ran a lot of system checks before the diver would get in the water. But again, we were able to actually run some of the hydraulics and stuff like that from the surface just by pushing the valves and stuff like that and making sure everything was working correctly before the first diver got in the water. But again, that first diver, like I said, giving you a thumbs up, we have a very sophisticated system. It basically has a very complex GFCI which basically sends a DC current through the system. If it doesn't get that back in milliseconds, it's cutting off the power. And so that's what is typically used in your high-powered ROVs. And so that's what's on this system as well. So here's kind of a video of what the end result was, testing underwater. You can kind of see the divers' umbilicals, which we had to definitely watch out for. Obviously, that's their breathing air and the communications and everything, and managing those hoses so you don't run it over. It's working with those things, but you can kind of see the diver putting his head on that screen, not even looking to his left and right, and just navigating that center line. The second diver gets a free ride and just manages and watches the reel, making sure there's nothing else happening. And he's basically standing on the emergency air tanks. That is a bailout on his back right there for emergency air. But again, we had those side tanks as well. But here kind of gives you a very good interpretation of how this goes down the tunnel. This is two rings connected together. You can kind of see the gasket material in between the joints to seal it up. And then the arms, holding those two sections and moving down the tunnel. Again, moving, somewhere around a half mile per hour, definitely increasing our production way past what we thought may be possible. So that was pretty exciting. And to have something, something new like that work as well as it did and not have any major issues was quite exciting. Again, we thought we would have those and we would have to, kind of pivot, but in the end, it was very small fixes, safety adds, put a handle here for the diver because he's going to hold on, those type of things. So we didn't have a lot we had a couple of design fixes, but other than that, like I said, it flawlessly went through its testing, which was pretty amazing. Some of the things that we needed to work with was like, how are the divers going to communicate? How are they going to manage their umbilicals? Where are they going to go so they don't get tied up in the vehicle? And one of the things that we knew would need to happen is traditionally divers are most of the time we're working with a single diver and they're not working together so that they don't need to talk to each other. But for this project, we knew these two divers were both going to be working divers. We knew for safety and production and everything like that them talking together instead of to the dive supervisor was essential. And so that's why we did the round robin communications in the project. And so the divers could talk to each other and hey, give me the wrench. Hey, you get the bolts. And that was a key differentiator to our success as well. Again, it was a lot of diver coordination and who's doing what. And, diver one's driving, diver two's doing this. And we figure that entire sequencing out to our final, basically writing down our final sequence. So this, like I said, we did some punch lists, testing stuff, and like I said, basically running the divers as much in that 3 weeks, as much times down the tunnel as we could to make sure that everyone was on board. So now comes this is where the rubber meets the road, is basically project deployment. So again, the first time Bert would go down the shaft, so how would it fit down the shaft? Would it fit like we wanted to? Because we couldn't mimic that as well. And again, we had a lot of success. Again, with our method of putting the football down first and ring assembly and really figuring that out. Our production was pretty slow at the beginning, but in the end, we were getting substantial production once we figured out all the ins and outs of the installation. To date, we've finished one tunnel, 500 feet, installed, grouted, and done. The second tunnel, the larger tunnel, the 12-foot inner diameter, is about 24% complete. We're going to finish it this year when we start diving here coming up in October. And so we'll basically complete it as well as grout it all in this season. We've seen productions of up to 4+ rings a day, which is pretty exciting, especially as you work towards your access, your production goes up. One thing that was pretty neat, there was a design challenge for us going for this larger tunnel, was the actual start of the tunnel is actually in a turn. So we had to customize some rings, chamfer them down to fit that, but basically what the design gave us and what the turn actually was were two different things. a lot tighter radius. You can see the design drawing in the bottom, but we knew that wasn't going to be the case. So we actually used our ROV division. We scanned the tunnel, and from that point cloud, we're able to see what the turn actually was and then design the rings around that. And as you can see, it's a progressive radius. It kind of turns, and it's all about the construction methods that were used to build the tunnel. And so we had to build liner plates, two different sets of liner plates that would fit that same thing. And so we had to basically fit that turn. And in the end, we didn't know if Bert was going to be able to bring the liners through the turn. And it was, so that we were able to do one ring at a time, cut the front section back a little bit, and we were able to do one ring at a time and work our way through this. So this was pretty much a great teamwork as far as the designer, the fabricator, and stuff like that to create these chamfered rings to get us around the turn. Like you said, some other innovations that you can see, these are some close pictures of kind of how it works. It's like a skid steer. We can plug in multiple different things. So that leads to later on, a cleaning device using an eddy pump or something like that to dredge tunnels with it. Making it autonomous is pretty much one of our big things. And that would be going to fiber optic, as well as changing over the controls to electric so that we could control it from the surface. So that that is kind of coming, and we've kind of been working on that as well. But that side of the business is, if you look at some of these intakes and how much sediments in these tunnels and being able to get it in there far enough to do it, this could definitely be the tool. If not, we would design and develop a new vehicle to just for dredging. So that's pretty exciting. So in conclusion, BERT can be applied to other rehabilitation projects, active water and sewer tunnels. Wet tunnel repairs can be conducted safely and efficiently. This is kind of the name of the game, is that we were able to provide a service without taking their tunnel out of service and repair it from within. So that, like I said, doing it without disruption to their service was key for the owner. And that's kind of where the exciting patent part of this comes and future business ventures. So with that, I'll leave it to questions.
Can you please elaborate on the need for grout lifts? Is wet grout heavier than cured?
Yeah, so hopefully I'm not muted here. So the grouting was, I could probably do a whole presentation on the grouting itself. We used an Amix plant that would deliver something like 5 cubic yards an hour. And so we basically went to a designer. We had them help us develop the grout. Obviously, it's going to be very cold temperatures, but ranging from 60 to 33. We basically had them develop the grout, but in the end, their mix wouldn't even mix in our mixing plant. It just wasn't, we didn't get the flowability. Our mix is consistent of bentonite, cement, obviously water, and then 2 admixtures. We had a high range water reducer and an anti-washout. Obviously, the anti-washout was the key to our mix to keep the grout stable. And we just kept working for weeks, making batches, making a lot of mess. And in the end, we were able to develop a mix that that temperature didn't really affect it that much. Its flowability was amazing. We now know that we can flow this thing 100 feet plus, without any issues. The grout lifts, we had to do 5 separate grout lifts because the loading on the rings itself. Because we were able to break it into 5 lifts, it dramatically changed the design of the liners and cut down the amount of skin thickness and that deal, which, from millions of dollars in stainless, we had a dramatic savings to the owner as far as the weight of the liners. So it was all about those 5 lifts. And then we actually developed I came up with a snorkel with basically screwed into the top 12 o'clock port, and then went to the very top of the tunnel with some holes, so that when we did that final lift, we knew that we had pure grout coming out that final lift flowing downhill, and we were able to ensure that we got full encasement of the liners. You said, is the wet grout heavier than the cured grout? I would have to go back and look at that. I would say, as the wet grout, Yeah, I'd have to go back and look at that. So hopefully that answers your question. But again, we had an overhauling success. We were very worried about the grouting operations, but again, we didn't overload the liners. It stuck to the design cliffs, and we were able to grout 50-foot bays in a day very quickly. So
Okay, here's another one. You mentioned an inflatable bulkhead for grouting. Can you discuss that more?
yeah, so that was actually a big part of the mock-up, was coming up with how are you going to hold that grout pressure, um, you know, something that's going to take up that 4.5-inch annulus, but still allow that grout pressure not to blow it out, right? I mean, we mocked that up and had several disasters, and in the end, we went to a more kind of expensive one, which was basically mechanical research. They make a lot of custom bulkheads, pipe plugs, all those type of things. And they came up with a very thick rubber, basically inner tube that goes into that gap when we get to a bulkhead. And then we actually use Burt, and I think I didn't really talk about it, but I developed a stand and a CG50 grout pump that goes on there hydraulically, and we hook it to the Burt. We fill a bag full of grout, which is only, I think it was 4 or 5 cubic feet. We fill that bag, we put it on the vehicle, we run it down to where the bulkhead is, and we use the hydraulic from Burt to run that pump, and we pump that rubber bulkhead, and it's thick. It's really thick and durable. We pressurize it to about 45 psi, which would seal off that bulkhead, and allow us to grout. So that's kind of they're not cheap, but they worked very, very well, and the friction between the concrete and that rubber worked really well to like I said, block off those bays.
Okay, thank you. Will there be a recording? Yes, there is a recording, Angelina. Where does it get posted?
It does get posted on YouTube within 2 to 3 weeks.
Okay, thank you. What was the duration of developing building Burt from concept to use on the first project?
Yep. So this is pretty exciting, and I think we can definitely improve on this. But from the first pencil on paper to ready to test at Oregon State was 10 months. Because of the things we've learned now, I think we can cut 3 or 4 months off of that easily, because of the things that we've learned through this process. And again, like, this Burt was built for, the 10-foot and 12-foot tunnel, but could we shrink it down? Could we make it bigger? Could we do other things? Knowing what we know today, should an owner come to us and say, hey, this is the problem we have, we would be able to develop a vehicle with Kelly Engineering very, very quickly. And it would just be a matter of, parts and getting overseas parts and maybe going to a US manufacturer for the subsea parts and stuff like that, and doing some of that ourselves would actually speed that up, because I think some of that process was just waiting on overseas parts.
Thank you. When making Burt remote controlled, how will you assure quality control?
I would say the answer to that question, I would say that could we do this ring installation autonomously? No, probably not. Could we dredge or clean or something to that nature? Absolutely. And that would just be as a matter of changing over to a fiber optic system, which is there's a control canister in there. Instead of like a serial cable, we would go to fiber optic and then change out the controls to electric. That would allow us to run all the functions that we would need from the surface. But because the liners are so intensive as far as bolt up and all that stuff, we would not be able to do that autonomously in this scenario. So, and I will say one thing that I was going to add that I didn't talk about, that I did want to talk about, was, and Renee can attest to this, we developed a VR system, a virtual reality system for this entire construction method, from putting Burt down the shaft and everything. we built, we worked with an animation company to do a VR, and that is now how we train the divers before they even go down into this situation. They run it through VR, and they said the reality of it is just so intense, and just like it is when they're down there, that we see the benefits of that, and we're looking into more stuff to use for VR. But they basically train and do the whole process, and they diver one and they're diver two, and we run through that whole scenario in VR, and then they go down to the operation. So that was a pretty cool innovation as well.
You mentioned that you made modifications primarily for safety. Can you share what those modifications were?
Yeah, absolutely. We had to, because if you've been around the diving world, the one thing divers like to do is break things. And so we had to definitely build a lot of covers over everything and increase the strength so that they could walk and jump and step off at everything. And so we made a lot of changes there. Some of the big ones, though, is what I didn't talk about is there's 2 full canisters on the side of Bert. If their little bailout on the back gives them, maybe 30 minutes of additional breathing time. But these canisters, they can be literally snapped off the vehicle. It has shoulder straps, and they can connect it into their mask should a catastrophic situation happen. And that will give each of the divers additional 3.5 hours of backup breathing air. So that was a big one. The other one was the investment of all the kind of the GFCIs of the system. So should a stray current happen, the tether gets broken or something like that, cutting off that power. And again, in fresh water, those risks of being in fresh water, high voltage is much higher, than that in the salt water that's normally, worked around. So those are some of the big things I would think.
While we wait to see if there's any more questions typed in, I'll just mention that our next committee meeting will be at DFI 50, the 50th annual conference in Nashville in a few weeks or about a month. So hope to see you there. And we also are hosting a Shotcrete short course in mid-November. And registration for that can be found through the DFI website as well. And that's in Georgetown, Kentucky. Now, I don't see any more typed questions. Shawn, did you want to close with anything?
Oh, no, Renee, I want to thank you for, having us come. This is awesome for the trailer construction group in Ballard. And like I said, we are very passionate about it, and hopefully it was informative and a good presentation with my lack of sleep. So thank you.
Yeah, thank you very much. I really appreciate it. And, this just shows ways to be innovative with engineering and think outside the box. And so thank you for highlighting that. All right. Well, thank you, everyone. Appreciate. Oh, wait, one more question. Okay. How does using BERT affect the overall project budget? Does it mostly save on labor, downtime, or materials?
Yeah. So if you look at the alternatives to replacing the tunnels, which was something that the owner was looking at, you're talking hundreds and hundreds of millions of dollars, and the schedule to do that and their overall issues with that. The money that was been saved on this repair, and we're basically pushing for other repair places they may use it since it was so successful. The downtime, the owner, we basically work on their schedule. They've had water main breaks where they tell us, hey, you can't work tonight because we can't shut it down, right? Or something like that because we got to transfer water. So that flexibility to be able to do that has been very beneficial for them. Again, the materials may be a little bit of high cost, to have the stainless, but pennies compared to new tunnels or something to that nature. And so I think that is where the success has been. And, you talk to the owner and they're very excited as the outcome of this. We didn't know at the time we were doing the project, we didn't know that we'd be developing this vehicle. We thought we'd be doing it, with traditional methods, and that could take a long, long time. But here, we're getting, 4, sometimes 5 rings in a night that's a lot of repaired tunnel sections in a very minimal amount of time. And doing it when they don't even need, when they don't even need the water. So it worked out very, very well for them.
I don't see any more, but I think your contact information is with the webinar link. So if anyone wants to reach out to Shawn, go ahead. Although I think you're on PTO, so may be slightly delayed. But yeah, thanks again, and thank you everyone for joining us today.